Hello, today we're going to be talking about calculus with polar graphs and equations, which is sections 10.3 to 10.4.
So the first thing I'm going to be talking about is polar coordinates. On the bottom is a polar coordinate system, and to the left is a section of the polar coordinate system. It's a diagram I took out of the book. So the polar axis corresponds to the positive x-axis of a Cartesian plane. O is the polar origin. Theta represents the angle between the polar axis and the line OP, and is usually measured in radians. R represents the distance of OP, and point P is represented as r theta, which is a polar coordinate.
Plotting polar coordinates. So the first point is 4, 4 pi over 3, which means that the angle between the polar axis and the line OP is 4 pi over 3, which is in the third quadrant. And r is given to us as 4, so the distance of OP is 4. The second point is 2, 5 pi over 6, which means that the angle between the polar axis and the line OP is 5 pi over 6. Distance is 2. And the third point is negative 2, 5 pi over 6. It is similar to the second point, except that r is negative 2 instead of positive 2, which means that it is plotted on the opposite quadrant, which in this case is the fourth quadrant. Basically, r theta and negative r theta are both on the same line through O and is the same distance from O, except they're on opposite sides of each other. Continuing on from plotting polar coordinates, if given a question that asks you to find two other pairs of polar coordinates, one with r greater than 0 and one with r less than 0, the first thing I would do is plot the point to see which quadrant it's in. So in this case, the point is 1, 2 pi over 3, which is in the second quadrant. And finding a point with r greater than 0 means finding a point that would still lie in the same quadrant as the original point. So it would still lie in the second quadrant. So r would still be 1, and I would subtract 2 pi from the original point, so it would find another point that would also be in the second quadrant, so the final point is 1, negative 4 pi over 3. And with r less than 0, r would be negative 1. So the point with r less than 0, it would lie on the quadrant on the opposite side of the pole. So I subtracted pi from 2 pi over 3, which leads to a final point at negative 1, negative pi over 3. Negative r theta usually represents the same point as positive r, comma, theta plus pi. The first polar curve I'll be talking about today is the circle, in which it is represented as r equals a cosine of theta or r equals a sine of theta, and a represents the diameter of the circle. In a polar equation of a circle that has cosine theta in it, it means that the leftmost edge of the circle will touch the pole, whereas for an equation with sine of theta, it means that the bottommost edge of the circle will touch the pole.
This polar curve is called a limison, which can be represented as r equals a plus or minus b sine of theta, or r equals a plus or minus b cosine of theta, where a is greater than 0 and b is also greater than 0. And in this case, I'll be talking about a limison with sine of theta in this equation. And these kind of limisons would be above the horizontal axis if the sign between a and b is plus, and below if minus. And below are a series of different limisons that are dependent on the ratio between A and B. So the first one is the looped, second is a cardioid, third is a dimpled, and fourth is a convex. And these are all graphs in which the sign between A and B is plus.
The graphs shown here are also limisons except with cosine theta in their polar equation. So the limison will be to the right of the vertical axis if the sign between A and B is plus, and will be to the left if it's minus.
So this curve is called a Rose curve and is represented as r equals a sine n theta or equals a cosine n theta, where a does not equal 0 and n is an integer greater than 1. If n is an even integer, then the rose will have 2 n petals, so if the equation is r equals a sine 2 theta, it will have 4 petals, and if n is an odd integer, then the rose will have n petals, so for example, if the equation is r equals a sine 5 theta, it will have 5 petals.
The last polar curve I'll be talking about today is a lemniscate. It's represented as r squared equals a squared sine of 2 theta or cosine of 2 theta, where a does not equal 0. A lemniscate with the sine function will be symmetrical to the pole, whereas a lemniscate with the cosine function will be symmetrical to the pole, the polar axis, and theta equals pi over 2. No matter what the a value is, it will look like one of these graphs, except it will differ in radius. So here is an example of a polar equation in which you have to graph it. So the first thing I did was identify it as a limison that is looped because the ratio of a over b is 1/4, which is less than 1. Then I plugged in some theta values to find some r values, and I plugged in some simple theta values like 0, pi, pi over 2, and 3 pi over 2. And note that the point -3/pi is not to the left side of the polar coordinate system, but it's at the right because the r value is negative. And I got the graph to the left.
This polar curve is a rose curve with 3 petals, and to graph this, I just plugged in some nice values for theta again, so I got some nice values for r. For example, I plugged in pi over 6, knowing that it would cancel out with the 3 in the equation to become sine of pi over 2, and I would get 4. And just in general, be careful when graphing polar coordinates that have the format negative r theta, and make sure to remember that it's always on the opposite side of positive r theta.
In order to convert polar coordinates to Cartesian coordinates, we simply use the formula x equals r cosine theta and also y equals r sine theta. These are both given by the definition of cosine and sine. An example of this would be to convert the polar coordinate 2, pi over 3 to Cartesian coordinate. The first step would be to solve for x by plugging in r equals 2 and theta equals pi over 3. So we simplify this to be 2 times 1/2, which is 1. To solve for y, we get y equals 2 sine of pi over 3, which is root 3 because sine of pi over 3 is root 3 over 2. Therefore, the coordinate point is 1, root 3. On the other hand, to convert from Cartesian to polar coordinates, we have to use the formulas x squared plus y squared equals r squared, which is the Pythagorean theorem, and tan of theta equals y over x, which is the definition of tan. An example of this would be convert the Cartesian coordinate -3, 1 to polar coordinates. First, plug in x and y into the Pythagorean theorem to simplify and get r equals root 10. Solve for theta by using tan of theta equals -1/3. Theta is equal to tan inverse of -1/3. However, we have to make sure that it's in the correct quadrant. So we know that tan inverse of -1/3 is a negative angle. We have to flip it so that it's a positive angle. Negative tan inverse of -1/3 is a positive number, but since we flipped the sign of that, we have to flip the sign of the radius so that it's in quadrant 2. So therefore, the angle is negative root 10, negative tan inverse of -1/3.
Now that you can convert between polar Cartesian coordinates, we can now convert between polar Cartesian equations. So the first example is converting a Cartesian equation to a polar equation. And since we developed earlier that x equals r cosine of theta and y equals r sine of theta, we can plug that in. And then we can factor out the r, which gives us r parentheses 5 cosine of theta minus 2 sine theta equals 1. And divide both sides by that value and end up with the r equals 1 over 5 cosine of theta minus 2 sine of theta. For the second example is converting this polar equation to a Cartesian equation. To develop a relationship between r, x, and y, I multiply both sides by r first, which leaves with r squared equals 4r cosine of theta, and plug in x squared plus y squared, which equals r squared, and r cosine of theta is x, so I just plug that in too. Then I moved the 4x to the other side and completed the square, and I got x minus 2 squared plus y squared equals 4. So the key to solving these types of problems is trying to find a relationship with the formulas x squared plus y squared equals r squared, y equals r sine of theta, and x equals r cosine of theta. Now we can solve for the slope of a tangent line to a polar curve. The question asks you to determine the tangent line to the polar graph r equals 2 plus 5 cosine of theta at theta equals pi over 2. First thing I would do is solve for the Cartesian values x and y. Since we know r, we can just plug it into the respective equations, and now we can solve for the derivatives of x and y. To solve for the slope of a tangent line to that curve, we take dy over dx, which is basically just the derivative of y all over the derivative of x. And since I'm trying to find the tangent line at theta equals pi over 2, just plug in pi over 2 into theta and we get 5/2. We also have to find the x and y values at which theta does equals pi over 2. So first thing I did was plug in pi over 2 into the r, and I get 2, so I can just substitute that in to the x and y equations for r, and then plug in pi over 2 into the theta, and I get 0 and 2 respectively for x and y. So my final equation is y minus 2 equals 5/2x. Common mistake is using dr over d theta to find the slope of the tangent line, which is incorrect because that only represents the rate of change of the radius as theta changes.
For the area inside of polar curves, the area of a single sector or pizza slice in a circle is pi r squared, the area of a circle, times the fraction of the circle, theta over 2 pi. Simplified, this is 1/2 theta r squared. where theta represents the change in the angle from one angle to another. Therefore, the total area inside of a polar curve could be represented in summation notation as sum from 1 to infinity of 1/2 r squared d theta. Integral notation, integral from theta 1 to theta 2 of 1/2 r squared d theta. An example of this would be to find the total area inside of the curve r equals 2 sine theta plus 2. We can look at the graph of it, which is a cardioid with reflectional symmetry about the vertical axis. This means that the area inside the cardioid from negative pi over 2 to pi over 2 is the same as the area from pi over 2 to 3 pi over 2. Therefore, our bounds of the integral will be from negative pi over 2 to pi over 2, and we will multiply the whole integral by 2. The 2 and the 1/2 in the formula cancel out. The total area inside of the cardioid is integral from negative pi over 2 to pi over 2 of 2 sine theta plus 2 squared. Simplifying this, we get integral from negative pi over 2 to pi over 2 of 4 sine squared of theta plus 8 sine theta plus 4. In order to integrate sine squared of theta, we have to remember the trig identity for cosine of 2 theta, and remember that sine squared of theta is the sine minus cosine of 2 theta all over 2. After expanding and simplifying, once we integrate it, it becomes negative sine of 2 theta minus 8 cosine of theta plus 6 theta, ranging from negative pi over 2 to pi over 2. Use the fundamental theorem of calculus with a result of 6 pi. Now that we've found the area inside of a polar curve, to find the area between two different polar curves, we have to use the same formula, but remember to change the bounds of the integral according to where the polar curves intersect. An example of this, find the area between r equals 2 sine theta plus 1 and r equals negative 2 sine theta minus 1. First, we have to simplify it by setting these equal to each other to find the points of intersection. Simplify to get sine theta equals negative 1/2, so theta is equal to negative pi over 6 and 7 pi over 6. In order to determine the bounds, we have to look at the graph and observe the symmetry of where the points of intersection are. Both negative pi over 6 and 7 pi over 6 are at the origin. When we plug these into the integral, they need to be the same area as the other areas. We have more areas, so the bounds will be from negative pi over 6 to 0, and we can multiply that area by 4. So if our integral is 4, integral from negative pi over 6 to 0 of 1/2 times r squared d theta, after expanding the inside of the integral and using the same cosine identity, the result is 2 times 3 theta minus sine of 2 theta minus 4 cosine of theta, ranging from negative pi over 6 to 0. After integrating, and use the fundamental theorem of calculus and subtract the values of theta after plugging in both 0 and negative pi over 6, and simplify to get 3 root 3 minus 8 plus pi. That is the total area that is overlapping between the two curves. Moving on, we have the arc length of polar curves. The arc length of a polar curve is integral from theta 1 to theta 2 of square root of r squared plus dr d theta squared. Common mistakes include mixing up the three different arc length formulas. However, it is important not to mix them up because they have different values. However, if one were to accidentally mix up the formulas, it would not make sense to use, for example, a polar equation in a parametric arc length formula. That is why it is important not to mix up the polar, parametric, and Cartesian arc length formulas. An example for polar arc length: find the length of the curve r equals 2 cosine of 2 theta from negative pi over 4 to pi over 4. We need to find dr d theta. We find this by simply differentiating r equals 2 cosine of 2 theta to get dr d theta is equal to negative 4 sine of 2 theta. Plug it into the arc length formula to get L equals integral from negative pi over 4 to pi over 4 times the square root of 2 cosine of 2 theta squared plus negative 4 sine of 2 theta squared d theta. Plug it into the calculator to get approximately 4.84. That is the length of the curve from negative pi over 4 to pi over 4.